Hey guys, welcome back. This is going to be the last video I do for Unit 5. And once we get through this, you should be able to get through those. I think it's only 3 more worksheets on Unit 5 anyways. So that'll wrap up the unit. That's pretty cool. So we're going to talk about something new. We're going to talk about frictional forces. We have talked about friction a little bit, but we have not calculated it. Every problem that I've given you so far, if we've had friction in a problem, I've always given you the value of friction. For instance, if I had a problem just like this, where I have this, whatever this object is, being pulled that direction, if I said, hey, this is a 10 Newton force, I've always said, oh, well, the frictional force is only 5 newtons or 4 newtons or whatever. So I've always given you that value. So now what we're going to be able to do is we're going to be able to calculate that value. Now, it's not anything more difficult than anything we've done already. It's just something different, something new. So it's something we have to get used to. Now, as we talk about frictional forces, one of the issues with this is that there's 2 different types of friction. So we have to be able to distinguish the difference between them. So, for instance, I'm going to do a little demonstration for you. I have this is just my kids' table that we have in the front room, and my little classroom set area right here is set up in my front room. So I'm invading the kids' space right now, so I'm going to use their stuff. And I have just a pillow that just comes off of my couch. But it was the best I can do. I don't have my lab supplies here, and I figured, hey, you know what? I'm looking around going, hey, this works. So basically what happens is this is going to act like this box right here. So if I'm going to pull this, now I'm pulling opposite directions because the force applied is going that way, and I'm actually going to pull this way. So if I pull this, of course, it's not surprising that it's not going to move. That shouldn't surprise anybody. And if I pull a little bit harder, it still doesn't move. And I pull even a little bit harder, and it wants to move up, but it doesn't quite move. That's because obviously it's friction that's holding it back. Now, we can draw a free body diagram for that. Now, I'm going to show you something though. It's going to be kind of interesting. First off, I draw my free body diagram. Of course, we have our gravitational force down. We have our normal force that is going to be up. And in this case, it's just like it's resting right here, Fg and Fn. They happen to be equal to each other. So whatever this value happens to be, if this is 2 kilograms, which it's not, but let's say this is a 2 kilogram box, that'd be 20 newtons, which makes this 20 newtons. Now, if I apply a small little force like this to the right, so this is my force applied, and it's just really small. That means I'm just pulling this and just going like this. Just a really small little force. Well, it's not accelerating this way. So that's telling me that my frictional force is going to be acting back with the same force. So these are going to be equal. That way it doesn't accelerate. Well, what happened when I increased my force? So I pulled this a little bit harder. Well, that tells me that this arrow is going to get a little bit longer, right? So this arrow gets a little bit longer. Well, it still didn't move. I still pulled this and it still didn't move, which tells me that this force right here, I should have wrote that where I can adjust this. That's telling me that this arrow right here is going to actually get longer as well, which is kind of weird because that tells me that my frictional force can adjust. It can change. So my frictional force responds to whatever I do. So if I pull a little bit, if I pull really softly, my frictional force is going to be really small. But if I pull a little bit harder, then my frictional force gets a little bit bigger. Let's say I even pull harder than that. Okay, I get it really close to the point where it's getting ready to start moving. So it's like, that's like that threshold of moving right there. Well, my frictional force is going to extend out and still be equal. So these are still going to balance each other out. Now, as we all know, there is a point where it starts moving. So if I get this if I pull, and increase my pull, and all of a sudden, bam, it starts moving. And you know what? I'm actually not pulling as hard right now. I'm actually not pulling as hard as I needed to get it to move. You guys have probably seen that happen before sometimes too. You try to push something across the floor. I push this pillow. It's harder to get it to start moving than it is to keep it moving. Move something across the floor, this whole table, I push it and go, oh man, this table's a little bit heavy. But once I get it moving, once it starts moving, it's a little bit easier to keep moving than it is to start moving. That's because there's 2 different types of friction. So if I go back to my free body diagram, there's going to be a point right here where you pull hard enough that friction can't match you. And that's because there's a limit to how much friction can hold when something's not moving. So what we have is we have something called static friction. So static friction is the frictional force that is acting on an object when the object is not moving. So when you're pulling on something and it's not moving, it's because static friction is holding it back. So if I wrote that down, so my first type of friction is going to be static friction. Static, like that, S-T-A-T-I-C, friction. And that's going to be labeled as force static. So just FS. That is the frictional force when something is not moving. So static, stationary. So I'm going to write not moving, right? So static friction when something is not moving. Okay, static friction can adjust. It will match your force. It will match. I'm not going to write all this stuff up here. I'm going to say it so you can rewind the video as many times as you want to. But there's also a PowerPoint that has all this stuff written up there too. I put the PowerPoint up on Teams so you can refer back to that. But static friction is for when something's not moving. Static friction will match your pull up until a certain threshold. And the other thing we can look at is static friction is dependent upon how heavy the object is, which tells you that it's actually dependent upon the normal force. Now, before back in Unit 4, I believe it was, I told you guys that there are two surface forces. I told you a surface, just like this surface can provide two forces. It can provide an upward, a perpendicular normal force, and it can provide a parallel frictional force. Talked about that last unit. So if a surface can provide those two forces are actually related to each other. So what we have to be able to recognize is that this perpendicular normal force right here is related to this frictional force. So if I increase the normal force, like if I put something on top of this box, then my frictional force is going to actually increase as well. If I double the weight of the box, so if I made this, instead of like 2 kilograms, I made it 4 kilograms, then my frictional force is going to double. Now, static friction, remember, can adjust. Static friction doesn't have a set value, but it is still related to your normal force. So the way we actually look at this is we can say that the force of static friction is going to be directly proportional, that's this funny looking sign, to the normal force. I don't remember if I've used this sign in class or not, but it just means directly proportional. It just tells you that if the normal force doubles, then the static friction doubles. If the normal force triples, then the static friction triples. And that means there's going to be a constant, a proportionality constant, that could make this actually an equation. So the way we do that is we say the static friction, force of static friction, is going to be always going to be less than or equal to, we have to use that less than or equal to because static friction will match your force up to a certain limit. We're going to use this cool Greek letter that is a cross between an M and a U. It's like a U, but it has this leg off the side of it, so it looks like kind of like an M. Well, in the Greek alphabet, we call this letter mu. It's actually spelled MU because it's a cross between an M and a U. Makes sense. So this is mu, Greek mu. That is what's called the coefficient of friction. This tells me how rough or smooth a surface is. So it's basically like a proportionality constant, so we can make this a linear equation, which is kind of nice. But it tells us the relationship between the static friction and the normal force. If we have a rough or dry surface where we have a lot of friction, something like your tires on asphalt, then this number would be higher. It's going to be between 0 and 1, so that'd be closer to like say 1. Whereas if we have something that's really smooth or a wet surface, so now all of a sudden we're on asphalt, like tires on asphalt, but it's like dry, what do we call it, black ice, then all of a sudden this number drops down closer to 0 because it'd be a lot more slick. So if this low friction, that's going to get close to 0. Higher friction, it's going to get a little bit higher, and we see things like closer to 1, like rubber on asphalt, it's going to be like a coefficient of friction of like say 0.8 or something like that. So that's basically the relationship. This is my formula right here for static friction. So again, static friction can hold up to a limit. Now once the object reaches that limit, like let's say we take this object and say that this is, I don't know, I think I said earlier I was saying 2 kilograms. So if I have a 2 kilogram object, which makes this Fg 20 newtons, which makes this Fn 20 newtons, then I just take that formula and say, okay, my force of static friction is mu s Fn. Let's say right here I have a surface that has a mu s that happens to be, I don't know, let's say 0.4, which is a pretty standard coefficient of friction. So if I take, my normal force, which is 20 newtons, and I take that times 0.4, that's going to give me a force of static friction of 20 times 0.4. That's going to give me, what is that, 20 times 0.4 is going to be 8 newtons. So I have an 8 Newton force. So if I have an 8 Newton static friction force, what that's telling me is that if I pull with 1 Newton, then the force of static friction, I shouldn't say equal, I should say less than or equal to. So my force of static friction can be up to 8 newtons. So if I pull with 1 Newton, then this is going to be 1 Newton. If I pull with 2 newtons, it's going to be 2. 3, it's going to be 3. 4, it's going to be 4. All the way up to 8. Now if I suddenly pull with 8 newtons, then all of a sudden, I'm going to break this limit and the object is going to start moving. So my force of static friction would withstand up to 8 newtons. Once I hit 8 newtons, then all of a sudden the object starts moving. When the object starts moving, well, guess what? We start acting against a different type of friction. And that different type of friction is called kinetic friction. So this is when an object is moving. So when an object is moving, we are going to be acting against kinetic friction. So static friction, static friction, static friction, all of a sudden, bam, it starts moving, and now I have kinetic friction. I'm acting against kinetic friction. Now, what happens with kinetic friction is it's almost exactly the same as static friction. We have the same type of idea. We can say Fk for kinetic friction, is going to be equal to mu k times Fn. So force of kinetic friction equals mu k times Fn. Notice it's an equal sign this time. It's not a less than or equal sign. Kinetic friction is a set value, and kinetic friction will always be less than static friction. So if I use this example here, let's say my mu s, my coefficient of static friction was 0.4, maybe my coefficient of kinetic friction might be, say, half of that, 0.2. So if my coefficient of kinetic friction is 0.2, then what happens is my coefficient of kinetic friction, or my value of kinetic friction would be 0.2 times my Fn of 20. So 0.2 times 20 would end up giving me a value of 4 newtons right here. So now let's say I have an applied force of whatever it happens to be. I don't know. It could be anything. In fact, if I get this to move, so if I pull this with, I don't know, I could pull with a force of 10 newtons. If I'm pulling with a force of 10 newtons, then I'm going to have an acceleration because I'm going to have 10 newtons here and only 4 newtons back here. The 10 newtons is enough to break static friction. Or I could even say something like, okay, I pull with 10 newtons so it starts moving, and then I lower my force, so my force only matches the 4 newtons, then I can say it's going at constant velocity. So a lot of times that's what we do. I pull, like in this case, okay, I pull, I get to 8 newtons, okay, now I just drop it down to 4 newtons. That way I can keep it going at a constant velocity. But if I go higher than 4 newtons, then it's going to cause it to accelerate. So I guess an example would be what happens if I pull with, some people will say that, hey, what happens if you pull with 6 newtons? If I make this right here 6 newtons, in fact, this would be a type of trick question that a lot of people could ask. If I gave this exact problem and I said, hey, you know what? What happens if I pull this box with a force of 6 newtons? Find the acceleration. Well, that's kind of a trick question, because if I pull this box that's stationary with a force of 6 newtons, then the force of static friction is big enough to withstand 6 newtons and the box wouldn't move. So my acceleration would be 0. However, if the box is already moving, then I can look at this and say, okay, well, if I pull with a force of 6 newtons, well, the 6 newtons force is bigger than 4 newtons if it's already moving. So I already broke this, and then I lowered my force down to 6 newtons. So 6 newtons is greater than 4 newtons. So I can look at that and say, okay, well, it is accelerating. And then you just go back and do Newton's second law. Okay, well, Newton's second law says F equals ma, and I have 6 newtons plus a negative 4 newtons equals mass of 2 kilograms. times A, I get an acceleration of, well, this is easy, 6 minus 4 is 2, 2 divided by 2, I have 1 meter per second squared. So I would have an acceleration. So that's how we would treat a problem like that. But it's tricky because you have to be able to identify, am I going to first break static friction, or you have to look at it and say, hey, I have an object that's already moving, so I don't care about static friction. Good part is some of those worksheets imply it already. They might say, okay, an object is moving like this, whatever, and then you just know, okay, you're dealing with kinetic friction. Or it might say, what's the minimum value of static friction in order to keep this thing stationary or whatever. So, you know, a lot of the problems, they kind of tell you what type you're dealing with, but, you know, there could be some trickier problems. If you took like my AP class or my pre-AP class, I would get into some problems where you would actually really have to identify this, or I might try to trick you guys. With regular physics class, we usually try to stay a little more straightforward and not try to trick you guys, especially right now when you guys are really trying to learn this, you know, online and whatnot. I'm not going to throw anything too crazy at you guys, so you guys can, you know, just kind of just go through this and go, okay, we're dealing with kinetic friction, so use this formula here, or we're dealing with static friction, use this formula here. You know, I'm going to box this one in because it's another formula you guys need. With that, I do have a PowerPoint that I put up that goes through frictional forces, has another example on there, it explains it a little bit more. There's a graph on there, if I'm not mistaken, that kind of talks about this whole thing where it's kind of weird between the like 8 and the 4 and what happens if you pull in between, where 6 newtons might not be enough to move it, but it could be enough to accelerate it. It's kind of weird. So look through the PowerPoint. Obviously, if you have questions, you can ask me. I'm online, you know, every morning, first hour between, you know, 8 and 9 o'clock, and third hour between 10 and 11 o'clock. So just make sure you can just, you know, I'm just sitting on my computer waiting for people to ask me questions, or you can email me at any point. I also put a formula sheet that you may or may not have. I can't remember who had it. I might have given it to you guys on a quiz or something like that. But either way, I put the formula sheet up there so you have the formulas for this unit as well. I made folders for you guys to turn in your work under the Unit 5 channel. If you go under Files, that's where the worksheets are. To submit it, you're going to see a folder that says Submit Work, and you can put your worksheets, just drop them into, you know, under that folder. You'll see your names in there. Just click on your name, the folder that has your name on it, and just put your work in there. Really, the only things that you're turning in right now are worksheets 3, 4, and 5. And if you have those done, just drop those in there. I will check them and just be checking off that you went through and did those worksheets, so I can give you guys points. Also notice some of you guys have gone through and done quite a bit of the con already, so that's awesome. So just keep with it. And like I said, if you have any questions, feel free to ask. Contact me either through Teams or at my email address at any time, and I'll get that message and get back to you. So with that, we're done with Unit 5. If you have, you know, like I said, if you have any questions, let me know. And you guys take care, and I will talk to you soon. Goodbye.